Welcome, everybody. This is now part three. For some people who are not as interested in the technical details, the mechanistic interpretability, how do you do it stuff, this will be the beginning of the more interesting part. So now we're going to talk about the high-level findings, the stuff that you don't actually need to know anything about, how they did it, um, in order to understand this. Um, I think for the pace that this group usually goes, there's a strong possibility uh, we won't get through because there's like 12 different examples, 12 different sentences, 12 different kinds of sentences. You can sort of see a sneak preview if you have really good vision in the little small screenshot. So the plan is we're going to start going through those today. I'm going to do a recap, and it's going to be an even faster recap than last time. Uh, and I was thinking to myself, if we do another session next week, if we do a part four, then I will challenge myself to do the recap even faster to see if I can somehow recap everything we know in 60 seconds or something like that. All right, so if you guys see my screen, um, so this is work that continues, work that started with the distill circuits thread. There have been these five major publications from the Anthropic team, starting with the mathematical framework for transformer circuits. And then this one is the latest, is what we're going to talk about. So as a way of background, transformers, these are decoder-only transformers. So Llama, GPT, DeepSeek, all of these models are decoder-only, and they have MLP layers and attention layers. The MLP layers process the information in a given token position, and you can think of the attention layers as the communicators that selectively bring information from earlier token positions to the current token position. And we talk about this residual stream as the residual path that if all of the layers output zeros, since they're additive, then the data would just flow straight through. So we can measure things along here. These are the hidden representation, the hidden states between the different layers at each token position. So the key idea here that underlies all of this mechanistic interpretability research is that the linear representation hypothesis, that the residual stream is a vector space, if you remember your math, and that different directions represent different concepts. Okay, so super short in linear algebra, you talk about that a, say, 4,000 dimensional space, you can have up to 4,000 linearly independent. You cannot have 4,001. You can have up to 4,000 orthogonal directions, and they can form an orthogonal basis. So what we've learned, though, is that when you have more things you want to represent than you have dimensions in your vector space, there is a way you can represent them, but what happens is you run the risk that you will have collisions between concepts. So here, sparsity is your friend. If you have different concepts like, I don't know, the Eiffel Tower and some super specific biology term, they're very likely not going to come up in the same sentence, paragraph, chapter, and therefore you can safely use them. And even though there is some possible confusion, you don't really have to worry about that as long as they don't come up in this at the same time. And so that's basically the idea that we have for LLMs, which is that in a two-dimensional space, the plane, like a piece of paper, you can only represent two things. But if they're sparse enough, we see easily in a toy example, they were able to get five, and you probably could do more. You could probably do seven. You could do whatever number of things. And the problem is, again, if any of these other things appeared in the same sentence, then when you add the two of those together, you get something weird in between. And it's going to cause interference and difficulty with reading these concepts. So again, going much faster than before. The transformers, we know that they do copying of information. And the key thing is that if you've heard of, in transformers, the queries, the keys, the values, and the outputs, there's four sets of weights. The Q and the K, the queries and the keys, they form the attention pattern, which is just a set of weights that add up to 1, but they cannot directly affect the numbers that are on the residual stream. They can only affect the values and the outputs, how much of each one from each token position is copied. Whoops, sorry, to the residual stream. So what we're going to see in this research is that for a given sentence, they're going to find the attention patterns from the actual LLM, and they're going to read those numbers. So it might be 0.1, 0.02, 0.5, 0.13, and they're just going to grab those numbers as constants, and they're going to not actually use the query key attention calculation anymore once it's been done once. For their analysis, they'll just treat this as a static pattern. So in today's discussion about on the biology of an LLM, we're going to look at how certain patterns with the MLP layers help do the calculation of the next token, the next word, in certain sentences. We will not be determining to any degree how the attention pattern got formed or general rules about the attention pattern. We're just going to be looking at attention in its frozen form for a given sentence. All right. So what is the technique they did? They basically said, we want to replace the MLPs in our LLM with something that instead of having lots of different directions all piled into this, let's say, 4,000 dimensional space, what we would like is we would like to have more easily human interpretable monosemantic concepts. So we're going to build a special type of autoencoder which will mimic the MLP, but instead of having something like whatever 16,000 activations inside of the MLP, we're going to build something maybe that has 40 million activations, with the intent that if we train it with the right loss function with an L1 type of penalty, then what we'll get is highly monosemantic activations, where in a given sentence, if they're talking about the Golden Gate Bridge, you'll see a non-zero number for one particular activation, which represents the Golden Gate Bridge, and you'll see zeros everywhere else. Life is not quite that perfect, but that's what you would hope for, is that you would get basically all zeros and just like, a single non-zero value. There may be more than one concept that a particular MLP is responsible for, so that could be a reason why you'd have more than one non-zero. But that's what we hope for, and that's what we're striving to build. And so this cross-layer transcoder is going to be predicting all the MLPs, and it's going to do it whether it's going to have monosemantic features for every layer. So we talked about that in a little more detail last time. We're just going to take that on faith right now. And then what we're going to do is, that was not enough to be able to do global analyses. So they said instead we're going to do analyses that are local to a given sentence. So we cannot say generically, this is what the LLM does in every situation with every kind of sentence. Instead, we're just going to say for one given sentence, what is it doing? So these circles represent the monosemantic features predicted, and these diamonds represent the errors between the predictions and the actuals. And once they've done and replaced the attention with just constants, replaced the normalization with just constants, then what ends up happening is this LLM now is nothing but linearly connected monosemantic nodes. And if everything is linearly connected, it is super fast and easy to calculate all the relationships. And so you can actually say that if Austin was predicted with a with a probability, let's say 0.95, you can actually see how much every single one of these other nodes contributed towards it having such a high logit and having a probability 0.95. You can see how much the word capital increased the value for this thing in layer 2 or that thing over there or whatever. And you can basically find the relationships between everything. And so then what they do is they find the high value relationships. They delete all the ones that are close to 0. And they get basically a graph that's a lot smaller than the one that would have millions, tens of millions, hundreds of millions of connections. And even then, many of these connections end up dead-ending, okay? So the word Texas is associated with the Alamo, it's associated with the Rio Grande, it's associated with being next to Mexico and next to the Gulf of Mexico and blah, 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 next to Oklahoma. Many of these connections are very strong, but will have no bearing on our prediction of the next token. So therefore, even though these are like dark connections, here you show them, we see them with dotted lines, they're going to prune those two. So they're going to prune anything that's close to zero, and they're going to prune anything that doesn't matter for this particular sentence's next token prediction. And then we'll end up with a small enough graph that if we combine similar things that are all related to Texas, similar things that are all related to the Golden Gate Bridge, similar things that are all related to acronyms, and so on and so forth, the graph might get small enough to where it's around 7, 10 nodes, and we can actually try to human interpret what the heck is going on. And I believe, is that my last slide? Yes. So that's the last slide in terms of the technique. What we'll see today is that they will use these shrunken down, highly simplified graphs to say, oh, well, if I boil it down to just these 7 nodes, then here's the pattern. Here's what's happening. Okay. They will then do experiments. They will do ablations, causal interventions on the real LLM to say, if this thing is so important, what if I zero it out? Does the next token prediction change? If this thing about Dallas is causing something about Texas and that's so important, what if I swap Texas with California? They will try a number of these experiments and, in my opinion, very convincingly show that for the dozen or so examples they gave, right? There's like whatever millions of sentences in their corpus, but for this dozen that they've shown, that the graph that they show as a concept very well seems to match the internal workings of the LLM because of the experiments that they do. All right. So that was my whirlwind recap and intro. So today, I think what we want to do is we want to go through these examples, and I'm going to flip from my slides to the actual web page.
Sorry, Ted, may I ask a question?
Please.
Of a previous slide, how did they do the ablation on the real LLM? Is there a way to map those features back to the weights in real LLM?
Yes, yes. Every one of these boxes represents the output of an MLP, a particular direction coming out of an MLP, or for convenience, there might be, say, 4 different ones that are all saying similar things. They're talking about, let's say, Dallas. Okay. So one might be about buildings in Dallas, the other might be about, the football team and whatever, whatever. But, uh, and so basically, we know that we predicted this direction from the MLP, and so we know exactly which layer, which MLP to go to if we want to make a change to that output.
Okay, I see, I see. Thank
Does that make
you.
sense?
Yeah, yeah.
Awesome. All right. Here we are on the web page. I'm going to scroll past. There's a bunch of introductory remarks and a section about the methodology that I just did the whirlwind tour. So here's our first example. This is a really good example. Multi-step reasoning. So they're going to analyze the following sentence. Fact, colon, the capital of the state containing Dallas is, and then they look to see what's the next token and how does the LLM get Austin, which is the correct answer, as its next predicted token. So in each of these dozen or so examples, what they do is they tell you sort of like what the prompt, what the situation is going to be, and then they actually summarize some of their findings in these bullets. I've found that for me, it's actually easier to jump to the actual graph and sort of see that before we start talking about uh, um, their findings. So I'm going to do it in that order for each of these examples, however many we get through today. Okay. So we have fact, the capital of the state containing Dallas is, and they found that fact, the, of, the, containing, that these words, of course, play a role, but that they did not have any of the largest activations, any of the most significant roles in next token prediction. Um, this chart here, by the way, is no longer uh, positionally or layer wise accurate. So when you see, say, a capital above state, that is not to scale anymore. Okay. It has to be the case that if something points from one thing to another thing, then the other thing must be on a layer above it, and it must be at that token position or later. But for example, it is entirely possible that these state features could be in layer 4, and if there's multiple, say, capital things they've lumped into a supernode, one could be layer 5, one could be layer 8, one could be layer 12. One of them could be at this token position, one could be at the word containing token position. Okay, so this is for sure a simplified graph that just shows the really strong weights that say that, oh, when you have a large value in the state direction or directions coming out of here, then just by virtue of the connections, because they're linearly connected, that causes a large value in the direction of, say, a capital to show up coming out of here. Okay. So does that make sense? And any questions about how you're supposed to interpret these? You should not interpret them visually like a map that is to scale. You should only think of them schematically in terms of things move up and to the right and ultimately wind up with a next token prediction in the residual stream. Okay. We actually can, for each of these, click here where it says view detailed graph. And then you can see uh, the individual tokens. And I believe here the layers are accurately mapped. You can see how high or low something is. So if we were to look at, let's say this state has, looks like it's about 5 or 6 features. See if I can click on these. So do you see this pink one got highlighted over here? Okay. So this state feature is actually not over the word state. It's actually in the is. It's in the last token position. Uh, this one's also, it's a little bit lower. This one you see is actually around what, layer 1, 2, 3, 4, 5 at the token position for the word state. Okay. Uh, this one's same token position, but an earlier layer. And this one, even earlier layer. Okay. So I'm not going to kind of go through, unless people have
Yep.
specific questions, I'm not planning to go through too many of the gory details. But the idea is that this graph maybe has 50 um, directions, monosemantic directions that were identified, and you can see fairly large number of different lines connecting these different 50 odd things. And so their goal was, this is still not very interpretable. So we're going to group things together that seem to have similar patterns. And that's this graph down here where they're grouped together. Then they redraw it schematically more simply like this. Yeah, question?
Yeah, I don't want to go deeper than you want to go, but on that diagram that you had, can we dive in a little bit? Like I didn't know when you were clicking on the little circles in state, what are the circles representing?
So these are individual monosemantic features that they found in an MLP at some layer.
Okay.
So remember, what they did is they built this special cross-layer transcoder that will do something like 40 million individual features for each layer of the LLM.
Okay.
And they're hoping that based on, so one of the things I was going to get to next that your question is the perfect segue for is, well, how do you know that if I click here, that this guy over here in layer 3 is a Dallas feature. Okay. So basically, what they do is they analyze based on our training data. Let's say it's, whatever, 100 million sentences. Okay. Which sentences had the largest activations, the largest values? Okay. Um, and they say, okay, here's our top sentences. And you can you can look and you can see, say, well, what are these what word, what do we have in common here? And what you'll see is like 3/4 of these words are Dallas. Okay. So this looks a lot like a input feature that fires whenever the token uh, is Dallas. Okay. You'll notice it's not 100%. So one of the key things to understand is they're presenting some conclusions here. Every one of these features, these monosemantic features, was hand labeled based on human judgment. So we could disagree. We could say we don't necessarily think that that was the right name for that feature. And we could disagree, therefore, then that you don't combine them the way you did. And then I would wind up with a different schematic for how this thing actually came up with the calculation. Okay. So, so given
Okay, so
that
these,
caveat, it's going to be very important that when we're done with the schematic and we've interpreted it, that we do a bunch of experiments on the real LLM to verify our understanding of what the model's doing. Okay. So the example that I give is usually it's like if you said that, the eyelashes are super critical for vision, then what you would expect is that if you trimmed my eyelashes, maybe I would have trouble seeing, but I would still be able to talk, walk, type, spell, do all of these other things, right? And if you trim my eyelashes and I see perfectly fine, there's like as if there's no difference, then that means that your hypothesis about how my body works is probably wrong. Okay. On the flip side, if you said, I think it's the optic nerve, and you snipped that in one of my eyes, and all of a sudden I'm completely blind in that eye, but I can still do everything else. I taste, I hear, I can walk, I can do math, then that's a pretty good hypothesis because the only thing that was affected when you modified my optic nerve was my vision. Okay. And you can do another experiment where somehow you inject electrical signals onto my optic nerve that aren't actually coming from my eye, right? And if I say, wow, when you injected these electrical signals, I started seeing bright lights and things like that. That's another confirmation that, yeah, this one thing seems to be very associated with what you said it's associated with. It seems to be associated with vision.
let me come back to that. See, Ashwin had a question.
Yeah.
Mhm.
Yeah, so I was just wondering, is this method of kind of feature labeling by a human annotator, does this make more sense for um things you could identify as like named entities, like Dallas or people, places, nouns, things, or is it also appropriate for more abstract things like verbs or adjectives or stuff like that?
It's definitely going to break down as you get more abstract.
Okay.
So, um, so you'll notice in the sentences that they choose for these examples, there tend to be objects and concepts and things they talk about that are pretty concrete. Like we're not going to get into more subtle things like irony or something like that. You know what I mean?
Yeah.
Um, so yes, that's absolutely true. And um, to uh, uh, um, I don't think we want to spend the time here, but it is potentially something you might want to do later to go back and look and see. Basically, some of these features, they're going to label them as a category called input features, and they're very distinguishable because basically, whatever they name them, that's just the word that appears a whole lot in the highest activations. Okay. It's
Yeah.
kind of interesting that we keep seeing Buffalo. I don't know how Dallas and Buffalo somehow get combined, but maybe this is actually a an incorrect feature And because there's actually more than 40 million concepts. So even though they tried to get monosemantic ones, they might actually still have two that are collapsed. But it's also possible that somehow in the internal representation, that is actually how the LLM represented things just by chance. Um, so this is one that's fairly easy to find. Another one that's fairly easy to find is if you it's probably an eye chart, you may not be able to see it, but there's a section here that says which tokens were most highly predicted when this node, when this feature had a large value. In this case, it's a bunch of Chinese characters. Okay. But sometimes what you'll see is that um, a particular word like baseball will be significantly promoted as the top token. Okay. And so then those they say are fairly easy to bucket. These are sort of output features, right? So we have input features, we have output features. Those are the easiest ones to sort of name. Because if you're like more than 50% of the time, the input word was something, then you say this is an input feature, right? And if you're crazy jacking up the probability that the next token is a particular word, then this is an output feature. But it's when you're in between the idea of a state or the idea of a capital of something, it's much, much harder. And this is where honestly I look at some of them. Uh, I don't know. Just try clicking on one here. Uh, if you look here, you'll see a whole variety of input words. Okay, there's one state here, but this is not an input feature. Okay. And then if you look at the words that it's promoting, it's nickname, admitted, nicknamed, US, admit. There's not necessarily a pattern here either. Okay. So then it requires more work to then say, looking at each of these sentences, not what word was it on, but what was that sentence generally talking about? Something most populous state in the US, its capital is Trenton, and its largest city is Newark. That's the first sentence. The next sentence is admitted to the Union on December 18, 1787. New Jersey is the fourth least extensive, but the 11th most populous. And then if you go through the examples, you're like, hey, all these sentences are talking about states. It's not on the word state, but what's going on, the vibe in that sentence is states. Okay. Uh, and so that's when the human annotator said, I'm going to say that this is a feature that's talking about states. Now, when they say state, that's sort of like the short name. That doesn't mean that the person thought that exactly it's talking about states. Maybe occasionally it's also talking about cities a little bit. Maybe occasionally it's also talking about countries a little bit. Maybe sometimes it's states and sometimes it's counties. You know what I mean? Like, so nobody's saying that this is a 100% perfect nickname for um, what that particular node is doing. And so I think last time I was talking a little bit about the Golden Gate Bridge. And so if you have a Golden Gate Bridge node, maybe sometimes it's talking more about tourist attractions. And maybe one of the other directions is talking more about um, architectural things in San Francisco. And maybe another one is talking about different bridges. And so you look and you say, well, 20% of the sentences were about other bridges, but the majority of them were about the Golden Gate Bridge. Okay. So these names you should not take super literally. They're just saying the closest majority vibe of this direction seems to be state related. Does that help?
So Ted, I think I can see the input features, the top activations. So that's where it's correlated with the input tokens in that token position, right?
So here, what they're talking about is which other node in this graph um, is is driving inputs into this node, and then this is what nodes does this node drive
Oh, I see.
Um,
Okay.
and so I believe, I don't know. I thought that sometimes we're going to see nodes that are unlabeled because they're just like, yeah, we didn't have time to get around to labeling all of these. Looks like in this one, maybe they did get around to it. Okay. Um, but so then you can say, what do these sentences all have in common? And then you may also sort of see a pattern that if for example, what we're going to see in this graph is that the capital and the Texas concepts both appear, then the Austin concept appears later in the higher layers of the LLM. Okay. So if you were sort of thinking that this feature was about capitals, and then you notice that the features that it's promoting are things like Austin and Sacramento and Trenton, and I don't want to be on the spot to keep naming state capitals, but then you might be like, now I'm pretty convinced this really is a capital feature because those are the nodes, right? So I could imagine it could be a little bit iterative where you're like, I'm not really sure if this is a capital thing. I'm not really sure if this is a Trenton thing. But then when you see that they're well connected, you're like, yeah, it looks like this makes sense that this is a Trenton feature and this is a Sacramento feature, and they're both connected from a capital feature.
Okay, so when you selected Dallas the first time,
Yep.
I saw a lot of activations. Like that word was in that column position, right? Dallas was in that, not every time, but a lot of times.
Yeah. Yeah.
And this is a node that's down early in
Yeah,
the
this is
model, right?
not the very first
But
layer,
yeah,
but
but
it's layer two.
yeah,
And so
yeah,
it's
yeah.
not surprising that this is basically processing the input.
Right, right. So
You
what I
would
want,
be you would be shocked to see an input feature way up at, one of the last layers. That would
right, and
be
so that's what I was
crazy.
wanting to look at is if we look at a node closer to the output. Is it related to the next token?
Yeah. So like this one is a say Austin feature, okay? And basically anytime you see a node labeled say something, what they mean is that it's an output feature. It's promoting the next token prediction of Austin.
Okay,
And so you would be shocked, I would be shocked to see a say Austin feature appear in layer three. That would be crazy.
right, right.
Yep. So you're
But it,
expecting input features to all be super low. Output features don't have to be super high, right? They could be closer to the middle, the whatever. And then these
whenever it
concept
figured it
features
out,
you
kind of.
expect very much to be sandwiched in the main body of the LM.
Yeah, yeah, yeah. Can you click a few more up near the top there? I'm seeing
Sure.
Austin follow that position, but not.
Now, this is for a graph for a particular sentence, which is, fact, the capital of the state containing Dallas is. So we're mostly going to see, say, Austin features. We're not going to see, say, baseball features, because those would all
Those
have
aren't
zero
ones, right?
value. So we'll see it in other sentences, but in
I
this
see.
one, most of the say blank. This looks like it says Texas related, say Texas. So this one might be a little bit of a say Texas feature.
Say Texas or a Texas output feature kind of thing.
Yeah, yeah.
Okay, okay.
And then
It
if
still
you,
takes quite a bit of reading between the lines to understand what's going on here.
it does. And I've looked at some nodes and I'm like, how did they get that this is a Dallas feature? I don't really get it, right? So, so again, we'll look at these. I think the experimental verification is super important because anybody could make valid arguments that their hand naming of the nodes was, what if this Dallas feature was only 20% of the time on the word Dallas, but 20 was still more than any other word, right? 10% Buffalo, 5% Sacramento, 5 this, that, 2, 1, right? So you're like, yeah, Dallas is the most common one. It's the plurality, but it's nowhere near half even. Is this really a Dallas feature? Maybe this is a city feature or a something else feature, you know, and I don't know what, you know. So you could definitely uh, easily poke at their names and possibly prove some of them wrong. The same thing that we saw in the detailed graph, when you hover over one of these rectangles, they give you the same kind of information. So here for Texas, they list all the things they lump together for convenience. So here they're saying there's 12 different directions that all seem to be varying forms of Texas related. Again, you remember some of them may be more geography related, some of them may be more political related, some may be more, I am having trouble thinking of other categories, but sound related, right? Some of the features may be a lot of Texas, but it's really about two-syllable words or words beginning with capital T or words that end in a certain sound so that they rhyme with Texas. You know what I mean? Like, it does not mean that these features are all 100% just the US state of Texas, you know? Um, but the good thing about this work is that they've really laid plain what they did so that anybody could verify and you can judge for yourself if you think that they stretched things. So again, if it's an input feature, you're going to see Texas, Texas, Texas appear a lot in the text. If it's an output feature, you're going to see um, it show up in the top next word predictions. In this case, you can see this is pretty strong. It has Texas TX, which is like the postal code abbreviation, Texas with a little t, Tex with a capital T, Austin TX lowercase. So, I mean, there is a lot of Texas going on here in terms of predictions. So this is about Texas, but this is also feature one is a little bit of a say Texas feature. I'm sure I will have no trouble. If I look at some of these other ones, you'll see, yeah, here's one. Feature three, the top tokens, there's nothing text, nothing, you know, Round, Tyler, College, Round, Bryan, Tyler, Temple, McKay, League, Richardson. Okay.
When you say feature three, what
those
is
are all places in Texas, though.
So then that makes sense that this is all logically Texas related, right?
Right. You get like Round Rock, Tyler, College Station,
Yeah.
Temple.
Yeah, I forget which article, but one of them you saw things like I don't remember the details, but it was like baseball, basketball, tennis, whatever, and then there was this LAC, there was this lack word in there, and they're like, if you didn't do your digging, but eventually if you did your digging, you would find that in this particular LLM, the word lacrosse was tokenized as two tokens, and it was lack and something else. Okay. And so, or more than two, but the first token was lack. And so they were like, we can't prove that this lack is for lacrosse, but given that the other tokens are baseball, basketball, bowling, tennis, golf, whatever, we we are interpreting it as it's yet another sport, you know. And so there's just a lot of that going on.
But Ted, when you're clicking on feature one, two, three, whatever,
Yeah.
what is that representing? Is there's a stack of Texas-like features there represented by that schematic bubble Texas?
Yes, yes. So
Okay.
these individual nodes at different MLPs, different layers, different token positions, okay, um, are what were we on? Texas?
Yeah.
Yeah. And so they just said these all seem to, again, you could just work with this graph,
Okay.
but there's still so many nodes, it's hard to sort of say a pattern. So then they grouped nodes into what they called supernodes, and that's these boxes here, where they say, here's 12 things I'm going to group together, that they're all various forms of Texas related. And if I take this graph and I draw it more schematically and less just like this, loose graph,
Okay. And that
then I
schematic,
end up drawing it like this.
okay. And that distillation is human judgment driven. Is that
Everything
right?
here is human judgment. The
Okay.
weights are not human judgment. The weights are the only thing that's like indisputable. Those are the numbers. Um, but which ones you decide to group together and blah 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 blah, that's where a lot of the judgment comes in. So that's a easy place where you could nitpick. Okay. Um, uh, so I think it was good for us to go into this level of detail to understand for the first one. Okay. If people don't have a lot of questions for the future ones, I don't think we need to, because I think actually the experiments are what do a very good job of supporting that they named things correctly. Okay. So one of the things they talk about in this article is they say if you had a sentence, fact, the capital of the state containing Dallas is, one possibility is that in its training text, this LLM has seen so many sentences and so many things about Dallas that it knows that Austin is the capital of the same state that Dallas is in. It just knows that, right? If you said, what is the capital of the state that San Francisco is in, the model might just know it's Sacramento. It doesn't necessarily even need to think about what state it is. It just knows that San Francisco and Sacramento have that relationship. Okay. And so in terms of like the stochastic parrots argument, you could say that there's just enough probability associated with it that the model has seen enough sentences that it can go straight from Dallas to Austin. Okay. That's one plausible way in which the next token is predicted. Another way in which the token could be predicted is the way that you might teach the concept of reasoning to, say, somebody in fifth grade, where you're like, well, first you should think about what state is Dallas in? And if you know that that state is Texas, then in a second step, you can ask yourself, well, what is the capital of Texas? And if you know the capital of Texas is Austin, then you would output Austin as your answer. And so that's what they would call two-step reasoning. Okay. And so what they're showing is that when they looked at these monosemantic features, remember, the original model just has these, I'm going to use 4,000, it's bigger than that. These length 4,000 vectors and all the different concepts are piled in there in a way that is very difficult to disentangle. The purpose of building the cross-layer transcoder is to split out that dense information into monosemantic features. Okay. So what they say is, yeah, we see a lot of muddiness, but we see a whole lot of features that seem to be about capitals. We see a whole lot of features that are about states, a whole lot of features that are about Dallas. When you have a feature that's about, when you have this set of features about capitals, they highly promote in a higher layer a set of features that promote the next token being a state capital, not a particular one, but either Sacramento or Albany or Trenton or Austin or whatever. Okay. And a similar thing happens with these state features, is that they promote the say a capital feature. The Dallas features do two things. They directly promote, excuse me, I love that this is interactive, but then I accidentally hover over something and there's the pop-up. It directly promotes this Texas set of features that we see in the model. And it also promotes the say Austin features. So that's this path over here. And we'll notice that the Texas features, they do a couple things, and they also promote the say Austin features, and they promote the token Austin itself. So they do two things. And then again, if you look at these lines, you'll see the say a capital feature probably promotes a whole bunch of different things. It promotes say Sacramento, it promotes say Austin, it promotes um, uh, say Trenton or whatever. Okay. Um, but in this particular sentence, the the say Sacramento feature is probably not getting support from anything else. So maybe it has, like a 0.15 value or whatever. But this say Austin is not only getting promoted from say Capital, it's getting promoted from Dallas and it's getting promoted from Texas. And so maybe this guy bumps up to a 1.5 or something like that. And so when you combine all of these things, other ideas like Sacramento wither on the vine and die, and say Austin keeps getting reinforced and gets bigger and bigger till the point where Austin is actually the next token. And I think we'll see in the next diagram, I think it had a 90 something percent probability. Okay. So it was not sort of like unsure and guessing Austin. It was quite confident that the next token should be Austin. Any questions before we move on to the experiments?
So Ted, it looks like if I see a bubble with like just a word, a concept, that says that they found kind of a correlation with the input token or something in the input sequence. And if it says the bubble says say something, then it's been more correlated with next token prediction.
Yeah, and things like Texas could be correlated to an input or just a general concept. In this case, it's more of a general concept. Although there may also be text, I'm sure there are Texas features that are associated with the word actually being in your input stream. Okay. Um, they use the convention say blank for features that strongly increase the probability of something being the next word. So what's cool about this particular two-step reasoning thing is that the word Texas never appears in this sentence. In fact, the capital of the state containing Dallas. When they labeled these features Texas, they labeled them based on their training corpus, right? So the training corpus is 100 million sentences, and they say, give me the top 100 sentences where this feature appears, right? So it's not labeled Texas because you know this sentence. It's labeled Texas because of how it appears generically in all possible sentences. All right. So that's the key thing is that when I hover here and you see these different sentences, these are sentences from the training set. Okay, or the evaluation set or whatever. But these are independent sentences that have nothing to do with this particular string at the bottom. This is evaluating, independently, when does this feature fire? All right. So if this truly is how the LLM calculated the next token being Austin, then you would think, like with my analogy of snipping the optic nerve, if we zero out some of these things, that should significantly change the prediction. They don't show it here, but if you zero out random other things that are not one of these 7 odd nodes, then what you would expect is it had minimal impact to the next token prediction Austin. I don't think they show that here. My guess is, though, they probably did do that. And it's a very easy experiment to just say, if you write some random values, it tends not to change the prediction of the LLM. So let's do some experiments. So the first thing we can do is we can zero out the say a capital feature. That's not one of the inputs. That's like one of those intermediate concepts that just shows up internal to the LLM. And so in the actual sentence, Austin was way up at 98%. Okay. If you zero out this thing, and in fact, technically they're not zeroing out because they're doing -2 times. Okay. So -1 times would be sort of exactly zeroing out. -2 is you're shouting a little bit. You've raised your voice a little bit to wipe it out. But then the next token, instead of being Austin, Texas is 76%. And then you see some of these other ones like located in Houston. And Austin did appear here at 1%. Not gone, but it's the 5th most probable token. So I would say that this one experiment is relatively good news to say, yeah, this supports that this is in fact an accurate graph because zeroing out, say, a capital had a very significant impact on the next token prediction. What if we zero something else out? Let's zero out the Texas features. You get a bunch of gibberish. You get space located not Austin at 6%, a double underscore, and then a whole long tail. Because remember, the vocabulary is like 50,000, right? A whole tail of things that are lower than 5% here. Okay. What if we wipe out the capital feature that appears fairly early on token-wise? We still have state, Dallas, and Texas, right? What ends up happening? Texas, 66%. Okay. Austin's completely gone now from the top 6 next tokens. What if we wipe out state and we keep capital and Dallas and blah, blah, blah? Well, now we're doing pretty well because we still get Austin at 91%. So it turns out that this was one of the least important building blocks because without state, you can still get, say, a capital and you can still get Texas, and those two can combine for, say, Austin. Finally, of these 6 nodes, the last one we can wipe out is the word Dallas. And if we wipe out the word Dallas, right, you would think that that could have a strong impact on all the things above. And so here, the say a capital feature is still quite strong. And so what do you get? You get Albany and Sacramento and Springfield and a bunch of other state capitals as the top token predictions. You also have the word not, which don't know why it's there, and I don't know what's the 5th most likely, next token or whatever. But I would say that all of these experiments significantly support the role of each of these rectangles, each of these supernodes, as being maybe not exactly what they say, but certainly at least relatively close to what they say, the role that it's performing. We have more experiments coming, by the way. This is just the first set. Any questions about this first set of experiments? All right. So what else could we do? We could swap it out. So we could say, based on a whole bunch of sentences, like facts the capital of the state containing Oakland is, we're able to isolate what are the California features that are very similar to the Texas features that we found. Okay? So what if we then take this Texas set of features, we wipe it out by a -2x, and we replace it with the California features we found from other sentences. But you'll notice we're not just saying California in our regular tone of voice. We are raising our voice a little bit because it's at 2x. Okay? We get from Austin 98%, we get Sacramento at 97%. I think this is a very powerful experiment. It's saying in this one location, and by one location, technically, Texas, the supernode, I think had, 12 features. So it's technically in these 12 places, okay? But basically in this one place, I swapped the directions for my Texas feature with the directions for the California feature and nothing else. I have not modified the LLM at all anywhere else in any way, shape, or form. And I went from 98% Austin to 97% Sacramento. The graph for calculating the next token might not be exactly this graph here on the left, but it's got to be true that this Texas business, that these features we found are highly, highly, highly influential in the next token prediction.
Question?
Yeah.
Any justification for the -2 and +2 as opposed to -1 and +1?
So if you remember, we deleted all of the millions, hundreds of millions of edges that had smaller values. There very well may be more Texas features in there. They're just not very loud. Okay. For example, maybe there's a feature that's all about the Southwest. And it is also about Texas, but it's not. So it didn't really get a really, large weight, and it didn't make the cut for this analysis, right? Maybe there's other stuff that's about the South that also includes Texas, right? Maybe there's some feature that's very barbecue related, but it's also about Texas. So we didn't zero out everything about Texas. We only zeroed out the top 6, 8, 12, however many features. So it might make sense that because we didn't exhaustively look for everything Texas out of the hundreds of millions of features that we identified, maybe we missed some. And so that's why you need to sort of raise your voice a little bit, because you didn't zero out everything. And similarly, we didn't find all the California ones. So we're going to kind of subtract the old Texas stuff a little bit louder and add the California stuff a little bit more.
So that scale may kind of be a proxy for how much of that concept did we actually capture in our pruned tree.
Yep. Yeah.
Interesting. So
and it's even possible that some of these other features promoted like pretty much the same exact Texas direction. But if we pruned them, then we won't be including them in the value for our Texas direction. We got the direction right, but how much of that we actually don't know, because we had hundreds of millions of nodes and we only measured, 6 or 12 of them or whatever.
Okay. So it's possible then that coefficient, you could change that. You could kind of experiment with that coefficient to see how sensitive is it to that particular coefficient.
Yes, and in this case, it did not work at 1x. The reason why it's 2x is because it didn't work well at 1x. Okay. I suspect it worked, but just didn't work super well. So they don't show them all in the diagrams, but they tried other states. Replace California with Texas with Georgia, you get Atlanta. They tried a whole bunch of different states, and it seems to work. What if you use something other than U.S. states? Did not work it worked, but it didn't work as well. So just what we were talking about, they actually deleted Texas at 2x, that's the same. But they had to shout, they had to scream British Columbia at 8x. So maybe this isn't really a state. Some of these other features like capital and state, maybe these aren't just capital and state. Maybe this is U.S. state. And maybe this is capital of a state, not a country, not a something else. Okay. But it seems to have some amount of overlap, because they were able to get it to work. They just had to shout at 8x. So they could get it to say Victoria with 92% probability, but they went up to 8x. If they picked different countries like China, they got it to work. It got it to say Beijing at 66%. Not as well. At 8x. And then they went to something that's not even a current state or country, the old Byzantine Empire. And they got it to say Constantinople at 93%, but they did have to shout it at 8x. So if we look at the article, there's a little bit more discussion about this business. So once again, this is probably a strong indication that this original circuit here is not 100% correct. The fact that they had to go 2x and 8x shows that this is not 100% correct. But the fact that it worked at all, I think, is actually pretty strong evidence that the graph is close to this, if not exactly this.
Ted, what exactly are they doing when they go 2x or 8x or whatever?
Yeah, so it means that you have a direction vector, Okay, so this is just a set of floats length 4,000, right? And they just literally 2x, they just double the numbers.
Oh,
So they're literally just
so
shouting. They're amplifying it.
okay, so that's like a probability or
No, this is on the residual stream. This is literally the
oh,
numbers inside the LLM.
oh, I see. So
Okay.
they're
Yeah.
putting their
So
finger on it, if you will.
yes. So imagine that it's just 2-dimensional instead of 4,000 dimensional.
Hmm.
Okay. And you've got a little bit of east. Okay. Like a 0.5 east. And you are writing north. Okay. If you write a 1, then what you're really winding up with is a vector that's 0.5 east and 1 north. And so it's actually like 30 degrees east of north. Okay. But if instead of writing a 1, you write a 2, then your resultant
Right,
vector, the direction now is only going to be ballpark 15 degrees east of north. And if you do 8x, now your vector is going to only be, 2 degrees east of north.
right,
Okay. So by shouting it, you get to, and remember, this is a residual stream. So the MLP outputs this value. You multiply by 8 times, you're sort of drowning out whatever other different signals were already on the
right.
residual stream. Okay.
Yeah,
So
so
that's why
shout,
shouting works better. If it weren't a
yeah,
residual stream and it were just like a direct connection to the next layer with no residual, you probably shouldn't need to do this because whatever direction you are is just the direction you are.
hmm,
Right? But in this case, because you're summing it with something that might not be 0, the louder you are, the more you're going to drown things out. And I believe if you go loud enough, like if instead of 2x or 8x, you went like 10 to the 15x, then at some point you're probably going to break the LLM. There's normalization layers, and so you might not, but there is a chance that you just break it
hmm,
because it's not designed for quantities that large, right? There might be other things that need to happen later that sort of still say like, oh, that's the word that you want to say, and let me suppress other things and let me erase some of my scratch work, and you know what I mean? And and
hmm.
and they just, I don't know. I You'd have to talk to somebody who's done a few more of these experiments, but that's the gist of it.
Okay, thank you.
Yeah, great question.
To
Uh,
carry this shouting analogy a little further, would it be correct to think of it as um, on this residual stream, there's lots of different concepts going on at once. Some could be shouted at one particular point, one particular node, while others are still whispering. Is that right? As long as
Yeah,
they're
and eventually the
they're
shouts
orthogonal.
will drown out the whispers. And I think one way to think about it is you've got a lot of different components, and what tends to work well is when you have destructive and constructive interference. And so if you have 5 people talking quietly saying the same thing, that's equivalent to a a regular volume voice. But if you only have one person saying Sacramento in a quiet voice, it's eventually just going to get drowned out.
Yeah, I guess I'm just wondering if there's a subspace where we're talking about capitals and stuff like that, geography things,
Hmm.
and we're starting to get closer to an answer. So people are talking loudly about Sacramento or whatever.
Hmm.
But in this residual stream, could there also be another subspace that's talking about emotion, and nobody's really has a strong feeling about emotion. So those are still there's still a direction there, but they're quieter voices.
Hmm. Absolutely, yeah. And so it requires more analysis to know that some things like emotion might be relatively orthogonal to Sacramento. And so it's easy to have those two conversations at the same time. But by coincidence, talking about whether you want hamburger or steak and the color green might interfere with each other a lot and cause problems. And so this is why you need trillions of tokens of training data, because it really needs lots of different combinations of words and sentences in order to figure out which things are safe to put near each other and which things have to be, they're very important concepts and they have to be very orthogonal, or I'm going to get green and steak, and that when you add those two together, you get this other direction, and all of a sudden you you um there's a sentence about a steak on a green plate, and then your next token prediction is Golden Gate Bridge, because that's what those two summed together to some intermediate thing, right? But if whatever we were talking about before, Sacramento and something else are very orthogonal, then they don't interfere, and then the Sacramento's unaffected by the fact that some of that other stuff is floating around on the residual stream. So we still need to learn more about which dot products are being done later to read out various things.
That's interesting.
Yep.
So thinking of the pre-training as kind of working out what parts of the subspace can be separate from others, where do concepts exist on that subspace.
Yeah, so you're going to imagine some very basic rules of grammar get etched very early.
Yeah.
And so they may not literally be frozen, but you can imagine they're going to get frozen. And then it has to decide, I think human emotions are really important for understanding the next token prediction. So I really, need to make sure happy and angry and these things don't have lots of collisions with many other things, because they seem to be really important, But maybe, mitochondria and Golden Gate Bridge are not terribly important things, and you can sort of shove them in some corner and they're near each other. And if ever so theoretically, if you find two directions that are very close to each other or whatever, like you could then say, oh, well, if I know that, let me purposefully write a sentence to see if I say I was reading about mitochondria while walking across the Golden Gate Bridge, see if you can actually fool it into a terrible next token prediction.
Yeah.
That's like
that's interesting.
Experiment.
I guess I always thought of the pre-training as more kind of, filling up the MLPs with facts and stuff like that. But this idea of working out what's this embedding space, if I can use that term, on the residual stream, that's really cool mental model. Thanks.
Yeah. And it's also learning attention, which we're not even talking about in this paper. And so then, it's how do you know what a pronoun is talking about when the antecedent was in the prior sentence 20 words ago?
Yeah, the relationship between them.
And how do you understand the fact that I'm in a rhyming poem, but the instructions to write a rhyming poem, that's the next example, were 100 words ago? And there's some very long-term relationships that you understand. I'm outputting JSON. I've been outputting JSON for the last 5,000 tokens. So there are various things that it's kind of amazing. Like there's a lot that the LLM needs to learn.
Hey,
all right,
Terry
thanks. You've had your hand raised for Thanks for waiting patiently.
Thank you. I have a question. Did they talk about at which step do they do this zero out and swap? Is it at the very last token position for the prediction, or there is also some swap
So what they're doing is, if we go back to, where did I have it? Nope, I went too far. If you go back to this detailed graph, okay, if I'm going to zero out the Texas stuff, okay, then there's 12 of these, and for each one of these, you'll see this pink one is at layer, I'm gonna call it 4 or whatever, in the last token position. Okay. But if I look around, I might find, here's one that you'll see is actually in the second to last token position at layer, I'll call it 9, I don't know, right? So basically, they know each of these features where they found it. And so then basically they can do the calculation and say that it was outputting a 0.5 comma, 1.1 comma 2 comma 0.3 whatever. And so just multiply that by -1. That's what they need to do. Or in this case, they did -2. That's what they need to add to the residual stream after the MLP for layer 9 at the Dallas token position. That's where they're going to add that thing. And for this one over here, they're going to add it in the last token position at layer 4, right? So do you see how they ultimately need to go back to this full graph to see the exact layer and MLP where it was being output, and that's where they write their modification.
Okay, I see. I understand.
Yeah. So they give us this nice simplified picture so that we can understand the basics of the wiring. But when they do the intervention, they're doing the intervention in the real LLM at whatever token position and layer the actual MLP did its
Okay.
thing.
Good. Okay,
Yeah.
got it.
No, that's a very important, so I'm glad you asked that. Yep.
And Ted, I'm not sure if I missed this, but is the subtraction and the addition in the same location?
Yes.
Okay, so they assume that Sacramento and Dallas both are in the same layer, same node. Is that right?
Oh, you're right. No, hypothetically, they're not in the same place.
Okay,
Yeah.
okay.
Yeah. I hadn't thought about that. I kind of assumed they would be, and maybe they often are, but you're right. Yeah, they could
Don't
be in
have to
different
be.
places. Yeah.
Okay, great.
Especially since this is not one single node. This is, 6 or, 4 or 12. It's multiple of them. But yes, they need to do it at the corresponding place. All right. So we have time for at least one more. Planning in poems. And so again, here you can come up with two theories as to how the LLM might write rhyming poems. Okay. So they give a prompt, we'll see in a second, but it says, I want a rhyming couplet. Okay. I want you to write something that rhymes. Um, he saw a carrot and had to grab it. His hunger was, and then like two sentences that uh, appear with fairly high probability are a powerful habit and like a starving rabbit. And I don't think off the cuff that these are both initially equally plausible explanations, but nevertheless, one could argue if one were in a certain stochastic parrot camp that this model is only predicting one word at a time, and it's doing it so well it has you fooled into thinking that it's actually kind of smart, but it's really just kind of dumb but brilliant at the one trick that it does. And so that this is what they call pure improvisation, is you just spit out one word at a time and then you're like, oh, I got to the end of line 2, I need a rhyme with grab it. Let me say rabbit. Okay. The other potential mechanism behind the scenes under the hood is that it's doing planning, and it's like, you know, not every sentence has a semantic completion that rhymes with grab it. You know, if the sentence was the baseball player hit the ball to the, your choice are outfielder, shortstop, second baseman. None of them rhyme with grab it, right? You're kind of screwed. So the question is, can we prove that it's actually doing planning? And they make a very convincing argument for the kind of planning that this LLM is doing. So here is their graph, slightly simplified, but basically a rhyming couplet. He saw a carrot and had to grab it. new line character, or comma, new line character. And what we're going to see is a whole bunch of activity happens on this new line character before the second line has even begun. And it's basically thinking to itself, ooh, what are verbs that rhyme with eat, it, et endings? And I have two candidates, rabbit and habit. And so the words rabbit and habit appear in the LLM before it has even started the next line. Then you have his hunger was like a starving, and ultimately what ends up happening is there's the possibility it would say habit, there's the possibility it would say rabbit, and rabbit gets promoted. And then it's the next token prediction. Okay. So this is the graph. We're going to see this again in other flavors. Let's do our usual kinds of experiments. Okay. So in this regular sentence, in the baseline sentence, rabbit came out at 81%. You might be surprised that habit, even though it doesn't make sense, his hunger was like a starving habit, doesn't make a lot of sense. It 19% next token probability. And percent is the convenient word. It's not necessarily calibrated, but when you do softmax, you get a 0.19. Okay, so what if we subtract rabbit very loudly at -10x? Then we can get habit at 95% and rabbit reduced down to 2%. And then actually crab, comma, it shows up in the next token predictions. What if we get rid of both rabbit and habit with -10x? Then you get crabbit, rat, savage, and bandit. What if we get rid of the rhymes with words ending with eat, et, it? You get his hunger was like a starving jaguar, cobra, lamb, or dragon, which are very semantic completions, but just don't rhyme with the previous line. So this is a good one. This one's like, hey, right? Like it seems like the idea of rhymes with words ending with eat, it, et is definitely a mechanism internal to the LLM. What if we erase rabbit and habit, but we add the word green? And then we get green, gremlin green, and rats green. They don't necessarily make a whole lot of sense to me, but you can see that you're shouting at 15x, you can get the LLM to say his hunger was like a starving green or a starving rat's green. So even though it doesn't really make sense semantically or rhyming wise, it is. And so also you can see that by deleting the rabbit and habit, we've basically overridden the rhymes with eat, it, et, even though we didn't explicitly zero it out, right? So this guy's job was to later up promote the words rabbit and habit. Its job wasn't necessarily to directly pick the next token. And so again, this is sort of confirmation that, do you see how this rhymes with concept? But then there's the rabbit and habit concepts. And so this guy does have a path here to say whatever, something, words ending with something T. It has a little bit of that. But this kind of confirms the graph in the sense that you get rid of rabbit and habit, and then maybe rats green is because of the T effect of this thing. So anyway, so this is a little bit of confirmation. And then finally, what is this? Oh, let's get rid of rhymes with eat, it, et, and do a different rhyme. Rhymes with E. 10x on both the delete and the plus. And then we get his hunger was like a starving chimpanzee, flea, or monkey, which very much are words that rhyme with E. So this seems to be some confirmation, right? We have a bunch of deletions and we have one replacement, like we replaced Texas with California. replaced the rhyme with a different rhyme, and we actually got a bunch of good semantic fill-ins that have a different rhyming strategy. There's more. Any questions about this first set of experiments? All right.
So, sorry. The thing that jumps out at me is something promoted the rhymes with part of this. It's like the instruction following part.
Yes, it's very hard to see, but basically the instruction that I want a rhyming couplet, and then that tells it, okay, I had he, don't need to worry about rhyming, saw, don't need to worry, carrot, and had, don't need to worry, to, grab, don't need to worry about rhyming, it,
Still don't need.
comma, new line, and this combination is like, boom, I now know what I need to rhyme with.
Right, right. That's really
Yeah.
interesting.
Yeah, this next chart is the one that really blew me away. So we have this rhymes with eat it at direction, right? We found that it's right 20 degrees northwest or whatever, right? They then did this thing where they did negative values for rabbit and habit and positive for green. So that's this experiment here, okay? So where we got completions of green, gremlin green, rats green. These interventions were done at the token position. These nodes all live at the new line token position. So if this LLM were like an RNN, then what would happen is this idea of words that rhyme with green or whatever would get added to our hidden state and would get propagated over the next 10 tokens until we got to the end of the second line, and then it would say, I need this, right? Transformers do not need to propagate the state token by token. Attention can reach back 10 tokens and grab something and pull it in. And what we will see on this chart is that this intervention where they did the two minuses and the plus on green has no effect if you apply it at any token position other than the new line. And in particular, all the places after it. This is not an RNN. So his hunger was like A. If green were sitting on, if rabbit and habit were just sitting there, then you could delete them and they would be gone and they would stop being propagated later forward. You can see very clearly there that somewhere it was not propagated here, but his hunger was like a starving. At that point, attention went back, presumably looked for the previous new line character and grabbed rabbit, habit, or green off of that residual stream and copied it forward to the current token position at some early middle layer so that then the rest of the LLM higher layers could calculate what's a good semantic completion that rhymes with whatever. Does that make sense? Like what I'm saying about the fact that this is all zero and this is this massive spike?
It's also having to know somehow, like, at what point do I need to grab back? Like, how many tokens do I output before I say, oh, now's the right time to go back and
Yes.
grab that?
So this analysis does nothing to understand that attention, right? We froze the attention pattern and we see that it did go and grab it from the new line position, but we don't really know how it knew to do that. Not from this particular paper, okay? But I love this chart. This says this is the difference between an RNN and a transformer. An RNN, if you deleted it anywhere in between, it would be gone. But a transformer does not have to just, and this would be true of Mamba, by the way, because Mamba is a fancy RNN. If you might not know exactly how to delete it, but if you deleted it, it would be gone forever. So then the next thing they look at is what about the intermediate words, not just the rhyme? And I'm not going to go into the detail, but basically, if you look at the earlier token positions, so his hunger was, and then it says something like starving are the next three tokens that are predicted. Okay. Basically, what you see is that the concept rabbit is appearing in the computation graphs for those token positions. Okay. And so it is actually it's not a super strong argument, and I realize because of time I'm not like going into the gory details. I'm waving my hands a little bit. But basically my oversimplification of this computation graph is that it's saying think of grammatical things that might help me get to a sentence ending with the word rabbit. That's what it's really doing, which is wicked cool. Um, I really, I really love it. So ultimately, there's a lot more that we probably don't really understand. And remember, they're hand labeling these features. So, uh, is there really a feature called approaching the end of a rhyming line? Is there a really feature called say a prepositional phrase? Is there really a feature called make a comparison phrase that ends in a noun? So like a something or other? These are probably approximate for what these nodes really do, okay? But nevertheless, it's just very cool. And I think they did some experiments on it. Yeah, so uh, in particular, if you zero out rabbit, then instead of his hunger was like a starving rabbit, it changes the sentence to it was his hunger was a powerful habit. And so that's how you know that it's thinking about what kind of sentence will end in rabbit. And you zero out rabbit, and it suddenly, and they didn't have to add habit. Habit was already there. So you zero out rabbit, and then, so yes. So the thing I was saying before about like replacing rabbit with green or whatever, it doesn't successfully, do that other thing. But that doesn't mean that rabbit isn't still in there doing other things. It is doing things. And so this is basically convincing evidence that it's um, it's planning way ahead that I'm going to rhyme. It's thinking about this heavy constraint that the word has to end, the next line has to end in something. And so it basically then orients itself around a candidate word. It's like, how can I create a sentence that's going to end in rabbit? And then this next section shows some additional planning um, that they do in terms of like the rhymes with. And so you, again, for time, but it's just like you saw Karen had to grab it. Oh, and then if you just let it complete from there, you get sentence like um, a rabbit's most desired habit. His love for veggies was quite a habit. A tasty treat, he was gonna stab it. Things like that. And then if you get rid of rabbit, then because it's going to now rhyme with habit, you can see the whole sentence structure changes. And so you get things like, so with his beak, he quickly nabbed it. Um, uh, let's see here. You zero out both rabbit and habit, and then you get things like delighted that the soil he had sent a gift. Here they change it with rhymes with E, the whole thing where we get chimpanzee or whatever, and you can see words, sentences like then added salt and pepper with glee. This zany rabbit, he was such a ham. See, the point is that there's a lot of knowledge that I'm going to end the sentence with a particular rhyming word that happens throughout the whole generation of the sentence. So before, when we said there's two simplistic explanations. One explanation is it just does next token prediction in a way that's super clever and then comes up with a rhyme when it gets to the end of the sentence. And this attribution graph seems to very much disagree with that explanation. It's very consistent with there's a heck of a lot of planning going on. Now, again, by planning, I'm not in any way anthropomorphizing human kinds of intelligence. You can still say it is pattern matching, it's probabilistic, but the patterns it matches are not just next token. The patterns are far more sophisticated in terms of let me plan out this sentence so that I can get a sentence that is both semantically meaningful and ends with the word rabbit. I think that's the end for, yeah, that's the end for this. So we'll for time we'll stop here. But hopefully this gives you a really good taste. We'll finish next week, and for me, this is super compelling evidence. Again, I'm not talking about consciousness. I'm just saying that the patterns, even if they are just statistical patterns, are really cool patterns with multi-step reasoning and with planning ahead. These are not just otherwise um, like very naive bigram looking patterns. You know, um, there's quite a lot going on other than, even though it is predicting the next token, it also seems to be thinking about what's going to happen 2, 3, 4, 10 tokens ahead, at the same time that it's predicting the next token. And that, for me, I find that to be a very plausible answer. I don't think you could ever get this good at answering things if you only ever really, really just thought one word ahead at a time. But this is some very concrete evidence with some very solid experiments to show the behavior. And like I said earlier, if you snip one thing, you know, if it doesn't have the effect that you want, then your explanation is not, your hypothesis for how things are connected doesn't really work very well. And they've done enough experiments that they seem to very well show that, like, in a very small number of places we modify the model and it interferes with exactly the behavior we predicted that it would interfere with. All right, so we'll stop here. We've got some more examples. We'll also see an example of addition of two-digit numbers where they show the pattern and you're like, that's a really dumb way to do addition. It works, but you're like, huh, that, you know. So maybe that will lead us to a slightly different training method, might get it to learn a smarter, more accurate, more extensible way of doing addition. And so who knows? Maybe that will be one of the things that comes out from this, is that people train it slightly differently and we get different patterns for how it does addition, and then the LLMs actually work better. So that would be a positive outcome from this research, even though, again, it's not explaining everything. It's just explaining a small number of very laboriously hand annotated examples.
I got a, I guess, like, point of discussion or question here, I guess, for just as a probably a good wrap up question. If we think about the implications of these experiments in the context of context window management and like needle in the haystack, garbage in, garbage out, kind of retrieval-y, rag-y kind of questions. I'm curious if anybody like has general thoughts or like something comes to mind of the paper that would be sort of relevant / actionable. And the reason I ask this is currently one of the sort of decisions I'm trying to help make is in the era of the 1 million context, full throughput, high fidelity, needle in a haystack is basically resolved kind of era. What, if any, retrieval augmented generation is appropriate if you presume you have a corpus of data that fits within the context window, essentially?
Yeah. I think generally speaking, on the biology is going to tend to be not too helpful for your question, because this is really focused on certain MLP patterns. Okay. And it's not really focused on how the attention pattern was formed. So a lot of the focus on something like long context and lost in the middle is are we getting good or are we not getting good attention patterns for finding those kinds of things?
Hmm.
So because this work really focused on the MLPs, it's possible there may be follow-up work that's super helpful, but that this work might not be terribly on point. Um, as a side note, I don't know if you ever read the writing in the margins paper, but I really liked that paper.
Hmm.
And um, so uh, you can do RAG, and you can do RAG and have like a summary of each um, chunk or document, that you shove into the context.
Well, it would be document, not chunk, right? Because you don't need to summarize the chunk. That's the point of chunking, essentially.
Oh, yeah, like if it's million, then yeah, right. But
Just to clarify for my
yeah,
understanding.
yeah, yeah.
Yeah.
But with writing in the margins, because of their clever use of the KB cache, now they're also able to inexpensively not just summarize the chunk, but then basically try to see. Um, sorry, they're summarizing the um, uh, based on your question. So they're not doing a naive generic summarization. They're doing a summary
Oh,
based on your actual question. Okay. So if you had like uh, the the operations manual for a 747 airplane, and you asked like, what is the correct washer to use with screw 1, 2, 3, 4, 5, 6?
mhm.
Okay. A summary of every chapter of the thousands of documents would not likely necessarily get you a perfect match.
Right.
Okay. But you do writing in the margins and you say, give me a summary specifically related to washers and screw 1, 2, 3, 4, 5, 6.
Interesting. I'm gonna have
Then
to
the
read.
page that actually has that information is likely to get you a screamingly good summary.
Right, yeah. That's super. I'm gonna have to go reread that paper, I think.
Yeah.
Yeah, the reason it seemed like it would matter here to me is because of all of these uh 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 like it seems as though like if we are like minus 10xing or plus 8xing or whatever, then that presumably should be a process that occurs naturally within the model as it is generating tokens. Yes, like it has to like have this vector space, and presumably it is doing the operation that the researchers are doing here, where they manually like inject a probability reduction or multiplication. But the reason they're doing that is to modify the end output. So presumably the model has to do that in order to arrive at an end output at all. So basically where my head is going with these experiments is, um, well, this things like this might tell me more about how putting like unrelated garbage into the context window um, will affect like the quality of the generation in a sort of, I guess, like thinking about it like fairly roundabout way, since this is basically inventorying all of the possible concepts and then trying to figure out which ones result in the thing at the end.
Yeah, I
Um,
mean, at the end of the day, I think it's a complex problem.
mhm.
If you remember the Rome paper, one of the things they did, they had one of the earlier causal interventions in the style of what we see here, and so they were able to, say something along like, fact, the Space Needle is located in the city of, and they were able to change it from Seattle to Rome or Paris or something like that. Um, uh, but it's tricky to understand because basically it's like, for my example, if you cut the optic nerve but you just inject electrical signals that you recorded from me previously or from some other person previously, whatever, I will see things, but it's not clear how to make me natively see those things with my actual eye, right? So that was one of the things that I heard from the uh, um, from the community in the Rome paper, they basically showed that um, you can, in effect, shout Rome loudly enough in the right place, and you can replace Seattle with Rome in a way that has relatively high sensitivity and specificity. So it'll change the Space Needle to Rome, but it won't change any other building to Rome. Okay, so that's pretty good sensitivity, right?
Mhm.
Specificity, right?
Yeah.
But the problem that people found was that paper actually didn't do anything to identify how you could actually change the LLM to say Rome. It didn't show how you could edit the LLM to output Rome for the Space Needle, right?
Hmm.
It showed what you want it to output to get the answer to be Rome, but it didn't show you what weights you would actually change in the MLP to make that happen.
Hmm.
And so that was one of the shortcomings, and to this point, people still don't know how to do that. So they proved that conceptually it's possible, but it's not clear. So maybe with these monosemantic directions, you might luck out into finding a Seattle and a Rome, and you might say, I can actually edit this column of weights and do that. Okay.
Hmm.
But most likely what you're going to find is you need this CLT because the facts about the Space Needle are sort of stored distributedly across multiple layers. They're not just in one
Yeah, that's
particular
the thing.
MLP.
It's like getting into the guts of like
Yeah,
how each layer is doing everything is going to be probably a
right. But now that we have the CLT, it will actually find the distributed representation
true.
and all that. Okay, but again, it's still. But so anyway, so that's my long way of saying that. Yeah, I think there's a lot of work to still understand some of the mechanisms, unfortunately. Um, and so I love the question, but I'm just saying I don't think we're necessarily that much closer to understanding how it processes these things. But I can say that generically, I think something like um, writing in the margins that A doubles the number of times you see the information because it's in the chunk and it's actually in the summary. So you've got it twice now. And then the summary is a lot closer to the prompt instead of it possibly being 500,000 tokens away. Um, in that paper, they filtered the summaries on ones that so there's a little bit of overhead for that, but they filtered them on which ones seem to have information relative to the question. So if you had 10,000 documents, it's not giving you 10,000 summaries. It's actually only giving you the summaries that meet a certain threshold.
Hmm. Yeah,
Okay.
I'm definitely gonna have to look at how
And
they.
so that paper I liked a lot because it just seemed very promising to me.
Mhm. Yeah, definitely. Cool.
And
Yeah,
again,
no.
that's not really directly related to the graphs that we've seen today, but it seems like, yeah, it can only help if you double the number of occurrences of the information and you
Yeah,
and you
yeah.
put it closer.
That is a fair point.
Yeah.
Okay, I think I'm going to stop the recording.